Hello, dear friends. I welcome you back to my YouTube channel. In our last session, we have discussed the types of nuclear reaction and we have also seen the mechanisms of a nuclear reaction. In today's session, we are going to discuss about the nuclear reaction kinematics. For that, let us consider a simple nuclear reaction. Some projectile, it hits the target nucleus X, giving rise to a product nucleus along with a product particle. Let us suppose that small mx, capital Mx is the mass of reactants, whereas capital My and small my, these are the masses of product nucleus and product particle respectively. Now, whenever we consider a nuclear reaction, either heat will be or energy will be evolved from that nuclear reaction, or a nuclear reaction itself requires some energy from some external source to carry out, right? So there will be liberation of energy or absorption of energy that will be takes place in a nuclear reaction. The reactions in which the energy is evolved is known as the exorgic reaction, right? The reactions in which energy is liberated, we call that reaction as the exorgic reactions. Whereas the reactions that require some amount of energy, right, that require the absorption of energy are known as the endorgic reactions. Endorgic reactions. So we can again divide the nuclear reactions into two groups as the exorgic reactions and endorgic reactions. For exorgic reaction, we don't need any energy to supply for that nuclear reaction, but in order to carry out an endorgic reaction, one must give an energy to the nuclear reaction, to this reactant particle and reactant nucleus, right? Now, if we apply the law of conservation of energy to this particular reaction, right? Because in any nuclear reaction, the energy should be conserved. So, applying the law of conservation of energy to this particular nuclear reaction, the example we have considered, what we can write down? We can write down the energy of this projectile particle, that is the rest mass energy plus kinetic energy. Rest mass energy plus rest mass energy plus kinetic energy, Ex, plus the energy associated with target nucleus, that is only the rest mass energy. The target nucleus is at rest, so it is not having any kinetic energy. That should be equals to the energy associated with the product nucleus and product particle. Both are moving to different directions after this reaction, when this reaction takes place, right? So this is the mathematical expression what we have obtained after applying the law of conservation of energy. Now here we have to define a, an important term associated with the nuclear reaction, that is the Q value of nuclear reaction. Q value of nuclear reaction. It is defined as the difference between kinetic energy of product and kinetic energy of reactant. So Q value of a nuclear reaction is nothing but kinetic energy of Y plus kinetic energy of small y minus kinetic energy of small x. This capital X is having zero kinetic energy. So in this way, the Q value of nuclear reaction is nothing but the difference between kinetic energy of products and that of the reacting particles. So we can write down Q to be equals to E capital Y plus E small y minus Ex. But we can again rearrange this Q value, this equation, Since we have obtained this equation from law of conservation of energy, we can obtain the expression for Q value of nuclear reaction in terms of rest masses of the product particle, product nucleus, target nucleus, and projectile particle. So this is an expression of Q value of a nuclear reaction in terms of rest mass of all particles that have been involved in that particular nuclear reaction. This is what we have obtained by applying the law of conservation of energy. Now let us apply the law of conservation of momentum, because during the nuclear reaction even the momentum should remain conserved. So applying the law of conservation of momentum, now here while applying the momentum we have to consider two directions. One is the horizontal direction, original direction of this projectile, that is horizontal direction, and another one is the vertical direction. So the velocity of this product nucleus, say that this velocity is nothing but the sum of two components. One is along the horizontal direction, let us say x-axis, and another one is along the y-axis, that is in vertical direction. So in horizontal direction, this law of conservation of momentum say that momentum of projectile particle, this is moving in x direction. So this is mx vx is equals to my vy cos phi plus small my small vy cos theta, where this phi is nothing but, I haven't drawn it here, but this phi is this angle by which this product nucleus has been deviated from x-axis. Theta is the angle by which the recoil particle or this product particle has been deviated from x-axis. So along horizontal direction we can write down mx bx is equals to this much. I have rearranged this term here. Similarly, along perpendicular direction, I can write down this equation. The perpendicular component of momentum is 0 because our projectile particle is moving only along the x direction. So its perpendicular, the perpendicular component of its velocity will be 0. So we will get the equation, this equation along perpendicular direction. So I can rearrange this equation 3 and 4. After rearranging and squaring and then adding these two equations, we will get the more simplified form of the above equation, wherein we have used the formula sin square theta plus cos square theta is equals to 1. And that's why we will get the expression like this. Now, the kinetic energy of particle, we can write down E equals to half mv square. So, this is the kinetic energy for projectile particle, for product particle, and for product nucleus. So, this equation would be rearranged in terms of kinetic energy of particles. So, what we will obtain? We will obtain such type of equation, right? Wherein we have written half mx vx square and this m to be written in again in the multiplication. So we will get this formula twice ey my instead of this my square vy square, right? We have multiplied and divided by 2 here, and an extra m was there. So this m I have written it again as it is. So the above equation becomes like this. Dividing everywhere by twice capital My, we will get this expression for kinetic energy of product nucleus like this. Now once we have obtained this expression for kinetic energy of product, we can obtain the expression for Q value of nuclear reaction, like Q, as we have said, it is the difference between kinetic energy of product minus kinetic energy of reactant. So substituting the expression for Ey that we have obtained here, we will substitute that expression here as it is, and we will get this equation for Q value of a nuclear reaction. This equation is well known as the Q value equation of a nuclear reaction. This equation is known as the Q value equation of a nuclear reaction. Once we know the value of theta, we can and the rest masses of all particles, we can calculate the Q value of that particular nuclear reaction. Now here we have to consider two special cases. One is the case of exergic reaction, which could be takes place even when Ex is 0, right? We don't need to supply energy to this reaction, this type of reaction to takes place, right? So this reaction can take place even when the value of kinetic energy of projectile is 0, right? So in this case, the Q value, substituting Ex to be equals to 0 in this equation, we will substitute Ex to be equals to 0, 0, 0. This term becomes 0, this becomes 0, and we will get the expression for Q value of nuclear reaction, exergic nuclear reaction, to be equals to Ey in bracket 1 plus mass of product particle divided by mass of product nucleus. So in this way, we can find out the kinetic energy of this product particle also by using this equation. Now, the more interesting one is the second case, that is the case of endorgic reaction. What is important from the point of view of exam in this Q value equation expression, or in this nuclear reaction kinematic session, is to obtain the threshold energy, the minimum energy to carry out an endorgic reaction. How much minimum amount of energy we have to supply for that particular reaction so that it could occur. So this is, I think, the important part of this expression, right? So let us consider the case of endorgic reaction, wherein the Q value of this endorgic reaction will be negative. Q value become negative only when the value of E, that is the kinetic energy of product, is less than the kinetic energy of reactant. So in this case, the Q value of endorgic reaction is negative, and the smallest value of kinetic energy of projectile particle, that is Ex, at which the reaction will take place, is known as the threshold energy, for which we have to obtain the expression by using our previous knowledge about the kinetic energy. Now we have the Q value equation. Let us rearrange that Q value equation in quadratic form, considering root of Ey to be equals to some x. We have to write down it in quadratic form, means we have to write down it in the form of ax square plus bx plus c. So this is our equation. If we have to write down it in the form of ax square plus bx plus c equals to 0, where x is equals to root of ey, right? Root of ey, then we will obtain the value of a, b, this coefficient a, b and c to be equals to a equals to 1 plus small my by capital My, b is equals to this much, and c is equals to this much, right? So the solution of this, we know well that the solution of this type of quadratic equation is equals to minus b plus minus root of b square minus 4ac divided by 2a. This is the solution. These two solutions we will obtain for this particular quadratic equation we have considered for this equation. Right? Now, from this equation, we can actually obtain the limiting condition, or we can obtain a certain boundary. Above that boundary, the reaction could occur and will have some definite solution. Below this boundary, the reaction doesn't occur, means the above quadratic equation will not have some real roots. If there are some real roots for the considered quadratic equation, means that the reaction will occur. But if there are no real roots for this quadratic equation, the above quadratic equation, then in that case we can say the reaction doesn't occur. And this boundary, we called it as the threshold point. How we can obtain this threshold point? By substituting b square minus 4ac to be equals to 0. Why? Because in that case, this root of ey will become negative. Minus b by twice a. It will become negative, means it will be an imaginary quantity. So, in that case, reaction will not occur. So, this b square minus 4ac to be equals to 0, it defines the limiting point. After substituting the value of b and ac, what we will obtain? B square to be equals to 4ac. B square to be equals to 4ac. So I have we can just rearrange this equation here, wherein this Ex I have replaced by the symbol E minimum, that is the minimum value of x, small x, that is projectile particle, at which the given reaction could take place. So we have denoted it by E minimum. So rearranging this equation, what we will obtain is the expression for E minimum, the minimum energy at which, the minimum energy of what? The minimum energy of projectile at which that particular nuclear reaction could take place. Now, in this expression here in denominator, there is small my plus capital My minus small mx. And for this expression, I can use the expression for Q value of that particular nuclear reaction. We have said that the Q value could also be expressed in terms of rest masses of reactants and rest masses of products. So, we can write down for this small my plus capital My minus small mx, we can write down it to be equals to mx minus q. So this E minimum, we can rewrite this equation to be like this: E minimum equals to this much. Again here we can find out more minimum value of this E, right? More minimum, how we can still obtain the lowest value of E minimum? We can say for the again lowest value of E minimum, this product particle, this will not go in any direction here, but it will go in a straight direction. Okay, the value of this Ex is so small that the product particle that has been formed is not having enough energy to go in on the other direction. It will carry its original direction. So in that case, for again minimum amount of energy of this E minimum, what we are calling it as the threshold energy, it is the it is the lowest value of A minimum at which the y is emitted only in the forward direction, that is theta is equals to 0. If we substitute theta equals to 0 here in this equation, we will get again the reduced form of E minimum expression, what we are calling it as now E threshold. So it is equals to this much. It has been observed that the Q value of nuclear reaction again expressed in terms of mass, because E is equals to mc square. This is an expression by which we can convert the mass into energy or energy into mass. So it has been observed that Q value of a nuclear reaction is much more smaller compared to the mass of target nucleus. Mass of target nucleus. So we can neglect this term, this Q value term here, and what we will obtain here as E threshold equals to minus my plus, that is the mass of product nucleus and product particle divided by mass of target nucleus into Q. But we can apply the law of conservation of momentum mass, that is mass of reactant, it should be equals to mass of product. So this mass of product I can replace it by mass of reactant. So this E threshold, it could be equals to minus Q, is minus Q as it is. Instead of mass of product, we can write down the mass of reactant divided by mass of target nucleus. So this is the expression we have obtained for the threshold value of energy, that is the minimum amount of energy, minimum lowest amount of energy, kinetic energy of projectile that is required for a nuclear reaction, endorgic nuclear reaction to carry out. So this equation says that it depends on the mass of projectile particle and the target nucleus. By using the value of the threshold energy and by using these masses, one can find out the Q value of endorgic reaction, and from this expression obviously that Q value will be negative. So this is all about the threshold energy of endogenic reaction. If you have any query, please feel free to ask me anytime, anywhere. Thank you.